Hello, I'm Thomas Kuehl, Senior Applications Engineer with Texas Instruments Precision Analog Linear Applications Group. Today I'm going to discuss electrical overstress of analog integrated circuits. This is an example of an analog integrated circuit that's been subjected to an extreme electrical overstress event in a circuit. In this particular case, the EOS that was applied to the device was so extreme that the device latched on, conducted very high current. The integrated circuit was melted, and the heat liberated was so extreme that the package cracked. EOS events may not be this dramatic. They may be much more subtle, but may result in damaging the integrated circuit. When designing a circuit, it's not only important to look at the electrical specifications, but also the absolute maximum ratings of the integrated circuit. In this case, this is an OPA 322 CMOS operational amplifier. If we look at the absolute maximum ratings, anything that exceeds these ratings is EOS. The supply voltage rating on the OPA 322 is a maximum 6 volts. So anything over 6 volts would be an electrical overstress. Anything applied across the supply pins that is greater than 6 volts would be EOS. The input signal pins are limited to a voltage 1/2 volt beyond the supply rails. So in the case of V+, we're talking about 6.5 volts, or if we had a 5 volt supply, that would be 5.5 volts. In the negative direction, if the minus supply is at 0 volts, we're talking about -0.5 volt. The input current is limited to plus and minus 10 milliamperes. Any current greater than that would be an electrical overstress. The output can withstand a continuous short to ground. If the output is biased at a different level, then it may not be continuous. Electrostatic discharge is a form of EOS, but it's an out-of-circuit EOS, and really comes about when we're handling and installing the integrated circuit. Internal to the analog integrated circuit are ESD protection circuits, and they are designed to handle this sort of event and protect the integrated circuit during the event. EOS, on the other hand, is where we're operating our integrated circuit. The integrated circuit is installed on a printed circuit board and is in use. Now in this case, this operational amplifier has supply voltages of +5 and -5 volts. But the input is being subjected to a pulse that is as large as 10 volts, 5 volts above the supply rail. And in the case of many operational amplifiers, they're not rated to a level that high. I show the internal ESD protection for an analog operational amplifier. There's the internal core, but then there's this additional circuitry: input protection, output protection, and supply protection. Across the power supply, we have this NPN transistor, which is normally off and is off at normal operating voltages. If the voltage becomes large enough during an ESD event, this transistor will turn on, clamping the voltage to a safe level across the supplies. We also have these input diodes and output diodes, which we refer to as steering diodes. They are designed such that an ESD voltage applied to any of the pins, if a subsequent ground of another pin or another potential is applied to the other pin, these diodes will turn on, one or more of them will turn on, providing for a path for the current associated with the ESD event. They will either clamp the voltage to a safe level across the integrated circuit, or they may steer the current through the clamp transistor, which will turn on and protect the device. An ESD event is very short, typically 200 nanoseconds or less, and the entire circuit is capable of dissipating the power associated with the event. Now, this same integrated circuit with this protection can be damaged during an EOS event, especially if the power supply transistor turns on. The inputs and outputs may also have clamps on the input, like we saw across the power supplies. In this case, there's no return back to the positive supply. But if the ESD event voltage becomes large enough, we can break down this transistor and provide basically a short between the input and the minus supply pin. On a negative going ESD event, this diode we see in the structure will turn on and clamp the voltage to a safe level. But in an EOS event, these devices, if the voltage is large enough, may turn on and can conduct current and be damaged in the process if the current is outside of the maximum input specification. Now, this is an example of an operational amplifier in normal operation where we have an intended signal, and now we have a signal being imposed on that intended signal. We've designated this as VG2. VG1 is the intended signal. Over here in the diagram, we see that VG1 has a range of minus 2.25 to plus 2.25 volts. That's the intended signal. VG2 is the transient riding on that input signal, and we see that the sum of them actually take the supply up to plus 3.25 volts, which is greater than the plus 2.5 volts applied to the positive supply rail. So we have an EOS situation here, both at the input and if that is coupled through the internal ESD protection to the supply pin, we can have that on the supply pin as well. If the current is limited to a low level, it's unlikely that we will damage the integrated circuit. The data sheet often provides guidance in terms of the maximum input current. As we saw for the OPA 322, that was 10 milliamperes. Some operational amplifiers have a value of 5 milliamps or a different value. A simple resistor in series with the input can provide a very simple, effective protection against an input EOS. If we take that OPA 322, for example, with its maximum, let's say we've got the input at 5 volts, so the maximum input voltage was a half a volt above that, or for a total of 5.5 volts. If I put 10.5 volts over here, I want to develop a 5 volt drop across the resistor with 10 milliamperes. And it's simply Ohm's law dictates what their resistor is. Usually it's just a matter of a few hundred ohms or kiloohms. We've got to be careful not to make that resistor too large because it does add noise to the circuit. This circuit shows complete EOS protection, not only of our supplies, but of the input and the output. And in many cases, this full EOS protection wouldn't be required in our circuit. Here I show the simple input resistor to limit the current. We can also add Schottky diodes or signal diodes to the input. Schottky diodes have a lower turn-on voltage than the internal steering diodes, but they can also be leakier and may contribute to the bias current, input bias current. A simple signal diode like a 1N40, 148 or something that will usually turn on a lower voltage than the internal diodes and have lower leakage current than the Schottkys. In the case of an inverting input amplifier, we've already got a series input resistor, and that provides good protection. When it comes to the power supply, and EOS in that particular case, we want to use a suitable TVS, a transient voltage suppressor, or a Zener diode. In the case of a dual supply operational amplifier, we would put one on each supply. The benefit of that of not only protecting against transient voltage, but is also that it provides a current path should one supply come up later than the other. Some analog integrated circuits are sensitive to that. This circuit also shows some clamps on the output and a series resistance. That often isn't required, but there have been applications where a voltage was getting back into the amplifier and causing damage. Hopefully the tips I provided will help you avoid damaging your analog integrated circuit. For more information, please see the following URLs.